Hi everyone, my name is Dan Deutsch, and I'm going to be presenting this work called A Statistical Analysis of Summarization Evaluation Metrics Using Resampling Methods. And this is work that I did with my collaborators Rotem, Dror, and Dan Roth. So in an ideal world, when we evaluate a new summarization system, we would have humans evaluate the quality of the summaries. But we know that this doesn't scale, it's very expensive, and it's slow. And so what researchers do instead is that we use automatic metrics to try and approximate these human judgments, which addresses some of the flaws of human evaluation. But because these automatic metrics just approximate human judgments, we'd like to be able to quantify how similar they are. And so how closely automatic metrics approximate human judgments is quantified by correlations, where we calculate the correlation between the automatic and human scores for a set of summaries. And this also allows us to decide which automatic metrics are better at approximating human judgments than others are. And so the standard methodology for evaluating a new metric X is to report its correlation value, and then argue that if that value is higher than the correlation for some other metric Y, then X is a better metric than Y. But this is sort of unsatisfying because this evaluation is only done on one sample of data. And so it sort of begs the question, well, how confident are we that the estimate of X's correlation is correct? Could we instead calculate a confidence interval? And how sure are we that X is actually better than Y and it wasn't just due to random chance? So can we do some sort of hypothesis testing? And so in this work, we're going to identify a set of questions that we might want to ask about evaluation metrics. Then we're going to propose some statistical methods to answer those questions. In the paper, we decide which among the methods that we propose are the most appropriate for summarization that I don't have time to cover here. And then we're going to apply these methods to real data, analyze the results, and see what we learn. So the way that you actually evaluate a metric is the following. So for a given system, you generate a summary for an input document, which is represented by this square here. You repeat this for a whole bunch of input documents, as well as a whole bunch of systems in order to get this matrix. Then you have a human annotator score each of these summaries with whatever aspect you'd like to evaluate. Then when we want to evaluate a new metric X, we score all of those summaries, those same summaries with X, and then we get these two parallel matrices, which we use to calculate the similarity. And the way that this is done is by the system level correlation, which quantifies how similarly X and Z score systems. And given X and Z, these two matrices, we calculate a system score by averaging over the columns, and then taking the correlation of these two vectors, either through the Pearson, Spearman, or Kendall correlations. The alternative method is called the summary level correlation, which quantifies how similarly X and Z score summaries for the same input document. So given these two matrices, we calculate the correlation for each column in these matrices, and then compute the average of these correlations, which is known as the summary level correlation. And so if you notice, the values of the correlations that we report are actually dependent on the set of systems that were selected and the set of input documents that were selected to do the evaluation. And so we might want to ask some questions. Well, what is the correlation of X to Z? And does X correlate more strongly to Z than Y does? But these questions are sort of ill-defined because we need to actually concretely say what assumptions we're making about the systems and the documents used for this evaluation. For example, we could assume that the set of systems is always constant, it's fixed, but there's some variability on the inputs. So the inputs are not always the same. We could make the opposite assumption and saying that the set of systems that we're choosing is random, but the set of input documents that we're always evaluating on is fixed. Or we could assume that both are variable. And we need to explicitly make these assumptions in order to make these questions that we're interested in well-defined. And so next, we're going to propose some statistical methods to be able to answer these questions. And the methods that we propose are based on resampling. And so here's briefly how they work. So if we wanted to use bootstrapping to calculate a confidence interval for this vector X, what we do is that we can resample from this original vector X with replacement, and then repeat this multiple times. And from there, we can plot the distribution of the means of these samples, and then calculate, say, a 95% confidence interval for the mean of the original value based on these results. For the permutation test, will allow us to compute a p-value to test whether the mean of x is greater than the mean of some other vector y, for example. And the way that this is done is that we actually sample without replacement by permuting which vector each pair of observations belongs to, and then calculating the difference between these two new vectors. And we repeat this multiple times and plot the distribution of these differences, and then we can compute a p-value based on the value which we actually observed originally. But if you recall, the statistics that we're actually interested in analyzing are functions of matrices, whereas what I demonstrated before were functions of vectors. And so the question becomes, well, how do we actually perform the resample for bootstrapping and permutation when the inputs are matrices? And so we propose 3 different ways of doing this for bootstrapping and permutation, and they're in parallel for each. And so I'm going to demonstrate the methods for bootstrapping X on the top, and then doing the permutation between the scores for matrix, the scores for metric X and metric Y on the bottom. So the first thing that we could do is that we could assume that the set of systems that are used in the evaluation are variable, but the set of input documents is fixed and always the same. And so when we do these resampling, there's only randomness in the set of systems, which for bootstrapping, this corresponds to sampling rows with replacement. For permutation, this corresponds to randomly permuting the scores on the rows between X and Y. If we make the opposite assumption that the systems are fixed, but there's randomness in the input documents, when we randomly resample input documents, this corresponds to randomly sampling columns in X for bootstrapping, or randomly permuting the columns between X and Y. And then finally, we can make the assumption that there's randomness in both the system and input documents, which corresponds to sampling both rows and columns or swapping both rows and columns in X and Y. And the different assumptions that we make will help us answer the different questions that we were interested in at the beginning. So for example, when we assume that the systems are variable and the input documents are variable by swapping rows and columns or sampling rows and columns, that helps us answer the question of what's the correlation of X to Z under the assumption that both the systems and documents are variable, as well as comparing the correlation of X and Y under that same assumption. And so the choice of sampling corresponds to a set of assumptions, which helps us answer the questions that we're interested in. So what we'll do now is that we'll apply these methods to real data and just analyze what we learn. So we're going to calculate confidence intervals and run pairwise hypothesis tests between a whole bunch of reference-based evaluation metrics under the assumption that the systems and both the input documents are both variable. So the set of metrics that we're going to use is on the right. And we're going to do this on the TAC data set, which is a multi-document data set with 48 input clusters with summaries from 58 different systems annotated with an overall responsiveness score, as well as the SumEval data set, which is a data set annotated from the CNN Daily Mail, which is a single document data set. There are 100 different inputs with summaries from 16 different systems annotated by a relevance score. And so the overall responsiveness and relevance scores are what we're going to use for our ground truth matrices Z. And so what we have here is we have these 95% confidence intervals for the system level correlation in orange and the summary level correlation in blue for the TAC data set on the left and the SumEval data set on the right. And the correlations are computed using Kendall's TACL. And so what we see is that the confidence intervals are very wide, which expresses that we actually have a high level uncertainty about what the true values of the correlations are. So if we report that the correlation, for example, of rouge is 0.7, it turns out we're not very certain that that value is actually 0.7. And the wide confidence intervals kind of have some serious implications. So I've highlighted the confidence interval for rouge 2 on the SumEval data set. And because of how Kendall's tau is calculated, we can kind of translate this confidence interval into the statement that we're 95% sure that rouge actually incorrectly ranks systems anywhere between 9 and 54% of the time with respect to humans. And so the most extreme interpretation of this result is that over half of the time when Rouge says one system is better than the other, it's actually wrong with respect to humans. And this is really bad because just about every summarization paper in part uses Rouge to argue that their model is better than some other model, whereas we're not actually sure how accurate that is. So here we show the results of a bunch of pairwise hypothesis tests. And a blue square means that the metric on the row is better than the metric on the column, and the statistical test had a p-value of less than 0.05. And if there's an orange outline, that means that that value remains statistically significant after we applied the Bonferroni correction. The pairwise tests for the summary level are on top and the system level on the bottom, with TAC on the left and SumEval on the right. And so the way that you can kind of interpret this is that if there's a lot of orange in the rows, that means that the metric on the row is good. If there's a lot of orange in the columns, that means that the metric on the column is bad. And so what we see is that BERT score actually does pretty well on both levels on the SumEval data set, and QA-eval does pretty well at the system level on both data sets. But unfortunately, we also see that a lot of metrics don't actually perform statistically better than Rouge, which is again a pretty disappointing result. So to wrap up this presentation, we proposed a set of statistical analyses for answering questions about evaluation metrics. And our analyses showed that we're really uncertain about how well automatic metrics actually correlate to human judgments. That being said, we were able to show that BERT score and QA-eval are actually better than the other metrics in some settings, but in others that no metric is really better than Rouge. And we recommend that anybody who proposes a new evaluation metric actually reports confidence intervals and runs these hypothesis tests, as well as researchers who are using these automatic metrics to evaluate their systems to be aware of these results, that the automatic metrics could potentially be very flawed. And so don't use these automatic metrics as sort of the deciding factor between whether or not a system is good or bad. With that, I'd like to say thank you for watching.